Hello and welcome. This is Cambridge O-Level Chemistry Paper 4, Alternate to Practical. The subject code is 5070. This is October-November 2023 paper, and this is variant 2 of this exam. So we'll be giving 1 hour to solve this exam in an actual exam environment. So let's start. First question, it says, a student investigates the electrolysis of of concentrated aqueous sodium chloride. Figure 1.1 shows the apparatus the student uses. Name the apparatus X. So see here, we have two inverted test tube, we have two electrodes, we have a container containing aqueous sodium hydro sodium chloride, and we have these graphite electrodes and these inverted test tubes. So apparatus X is an inverted test tube, or actually it is a test tube. Okay. So moving ahead, it says, give a reason why iron electrodes are not used in the electrolysis. So remember, we have concentrated aqueous sodium chloride. So we have here NaCl, and this is in its aqueous form. So when we are doing the electrolysis, we'll be getting sodium ions, we'll be getting chlorine ions, we'll be getting H positive ions, and we'll be getting OH negative ions. So these all ions will be there in the electrolysis process. So when our electrode will be of iron or Fe, iron, when he have iron electrode, so these negative electrons uh, or the negative ions, for example, chloride ions, OH negative ions, they basically go and react with these and they basically start damaging these electrodes. So basically that is why we are not going to use uh, iron or any other metal electrodes that can react with these ions, or basically we use inert electrodes. So the reason why, so the reason is that iron electrodes are not inert and go under chemical reactions. Okay. Then part C says chlorine gas is produced at the anode during the electrolysis. Describe and explain one safety precaution that student takes during the electrolysis. So remember, if we are talking about chlorine gas, Cl2 gas, this causes severe irritation in eyes. The safety precaution, um, this whole setup or this whole electrolysis setup needs to be present in a well ventilated area or a fume hood that has a air suction out of it. So safety precaution, uh, ventilation should be good. Use fume hood. Also wear protective glasses. Okay. So explanation why? So because Cl2 or chlorine gas is toxic and harmful if inhaled. So that is how, or we can, um, that's the reason why we have to save ourselves while working with chlorine gas. So the part D, it says a different gas is produced at the cathode during the electrolysis. Name the gas produced. So remember, at the cathode, or basically the negative electrode, at the negative electrode, sodium ions are going and H positive ions are going. So H positive ion basically converts to H2 gas over here because sodium doesn't, uh, sodium ions do not convert to sodium metal, and that's not happening here. So the gas that is produced, that is hydrogen gas. Description of the test, remember hydrogen gas produces a popping sound in a split. So write the test. So bring a lighted splint to the container having H2 gas. Popping sound is heard. Okay, this is the test for this gas. So moving ahead, for question number 2, it says sulfuric acid or H2SO4 is neutralized when it is added to sodium hydroxide or NaOH. Then the equation reaction or the equation reaction is given. It says the reaction is exothermic. Then it says P is 1.25 mole per decimeter cube of sodium hydroxide. So this is your P. This is 1.25 mole per dm cube. Q is dilute sulfuric acid. So this is your Q. A student determines the concentration of sulfuric acid. So we have to find, or the student is looking for the concentration of sulfuric acid. The student does 6 experiments. The student number 1, step 1. It says uses a volumetric pipette to add 25 centimeter cube of P to a plastic cup. Okay, so they have taken say a cup. They have added 25 centimeter cube of P. Then it uses a measuring cylinder to add 20 centimeter cube of distilled water to the plastic cup. So then it adds 20 centimeter cube of H2O water into. It stirs the mixture and the thermometer and records the temperature to nearest 0.5 degree centigrade, or basically measures the temperature. Or you can say temperature is measured. Then it records the highest temperature reached, empties the plastic cup, rinse. Oh, sorry, missed the step 4. So it says that uses the burette to add 5 centimeter cube of Q. Basically, it adds now acid Q, 5 centimeter cube of in volume. That's the volume of acid used. Stirs the cup, records the temperature again, empties the cup, rinses it with water. Repeats the steps 1 to 6 with different volumes of distilled water and Q so that the total volume in cup always remains 50 centimeter cube. Okay. So in experiment 1, it says volume of P, volume of water, volume of Q, temperature. So the rise in temperature is basically the difference, rise in temperature between T final minus T initial. So this is your T uh, final temperature. This is your initial temperature. So the difference here is 2.5 degrees centigrade. Then part 2, 25 centimeter of P, 15 of water, 10 of this. Then temperature rise is this. Similarly, 25 of this, 10 of this. So the remaining is or will be 15.0 because the total sum of P plus H2O water plus Q is equal to 50 centimeter cube. So this is then 7 centimeter cube of water, 18. The temperature is 8, 25, 5, 20. This 25, 25, so 0. This. So part 8 says complete table by filling the three missing values. So we have filled in the values over here. So 0, 15.0, 2.5 with the values. Moving ahead, it says part B, parts of the thermometer used in experiment 3 are shown in figure 2.1. The liquid level inside the thermometers are missing. Complete figure 2.1 by drawing the liquid level to show number 1, the initial temperature in experiment 3. So let's see, the initial temperature in experiment 3 was 23 degrees centigrade. On experiment number 3. Experiment number 3, the initial temperature. So this is our experiment number 3. The initial temperature is this 25 degrees centigrade. So let's see, let's go and draw. This is my line of 25 degrees centigrade. So it would be something like this, liquid, or because the mercury inside the thermometer. So technically now the mercury is not used in the modern in thermometers because of its um, toxic nature. So this is how you'll be going to label this. Then the highest temperature reached in experiment number 3. So highest temperature reached is 32.5. So this is again 32.5. 32.5 would be somewhere here. So this will be your 32.5 line. So it would be something like this. There would be a bulge, and so you have to show this bulge. So that will basically show that yes, you are, because there is a liquid inside this thermometer. So this is 32.5 degree C, and this is your 25 degree C. Okay, so this is how you make this. Then it says part C, draw the graph of temperature rise against volume of Q on the grid 2.2. So over here, plot should start from point 0, 0. There is no temperature rise when no Q is added. Plot the temperature rises and volumes of Q from table. Temperature rises and volumes of Q. So rise in temperature. So we have to plot this and volumes of Q and this. So this is the value and this is the value. So first, 5 centimeter cube, the temperature rise is 2.5. So 5 centimeter cube, temperature rise is 2. So this is 3, somewhere between here. So this is my first point. This is my first point. Uh-oh. Okay, then our next volume is 10. Next volume is 10. My volume rise is 5. Then we have 15 and 7.5. Okay, so next point, we have volume rise is 10 and volume is 10, temperature rise is 5. Then we have 15 and the volume rise is 7.5. 15, 7 to 4, somewhere here, 7.5. Then we have 18, 8, 20, 8, 25, 8. So then all of the next three values are 8. We have 8 at 20. We have 8 at 25. We have also 8 at 18, 15, 16, 17, and 18. So we have value of 8. So these are our values. Then it says draw a straight line of best fit for the last 3 points. Okay, so now basically what I'm going to basically change the color so that you'll be able to understand it better. We have to draw two straight lines. Draw a straight line for the first 4 points. So let me see. So I don't have a ruler. Make sure you have a ruler. And for the first 4 points, so the first point is 0, 0, 1, 2, 3, and 4. So first 4 points. So you make a straight line and extend it. Okay. Then this is your, you can call it as line 1. And then you have to draw a straight line, that is your line 2. So something like this. So line 2. And this is the your intersection point. Extend the line so that they intersect. So this is your intersection point. And remember, in then such you can say questions, this point where your temperature rise starts to level out, or there is no further increase in temperature, that means that this is the volume of Q that completely neutralizes the base, or you can say volume of Q, also acid that neutralizes the base P NaOH in the solution, and that is what we will be using. So that's maybe the next part of it. So that says part D, the point where two lines intersect indicate the volume of Q that exactly neutralizes 25 centimeter cube of P. So remember, P is our base, and that was NaOH. Q was our sulfuric acid, H2SO4. Determine the volume. So if we're going to see, so this volume is, so we'll come down on your graph, you'll come down and you will mark this point. It comes out somewhere here. It turns out to be where is my pen? So it turns out to be 16 centimeter cube. So you'll go over in the next point, and so let me change it to red again. You'll go again, and it comes to 16 centimeter cube. Then in part E, it says P is 1.25 mole per decimeter cube aqueous sodium hydroxide. Use your answer in D to calculate the concentration of sulfuric acid. Okay, the concentration of sulfuric acid. Remember, 2 moles of sodium hydroxide, 1 mole, 2 mole, 1 mole gives you the answer. So P 1.24 5 moles per decimeter cube of sodium hydroxide. So let's try to do it. So 2 mole of NaOH requires 1 mole of H2SO4. If we have 1 mole of sodium hydroxide, it will require 1/2 mole of H2SO4. How many moles we have? So we have 1.25 moles per 1000 centimeter cube. Remember, 1 decimeter cube is equal to 1000 centimeter cube, and the volume of NaOH that is used, the volume used is P is 25 centimeter cube multiplied by 25 centimeter cube. So this will give you the number of moles that are used. So this comes out to be 0.03125 moles of NaOH will give 1/2 is 0.5 multiplied by 0.3125 moles of H2SO4. So the number of moles of H2SO4 you will get will be moles of H2SO4 will be equal to 0.1015625 moles of H2SO4. And then you have to give the concentration. So remember, this is the number of moles and volume of Q or H2SO4 is, remember, above 16 centimeter cube. Okay, so the concentration will be number of moles divided by volume. Okay, so this gives us 0.015625 divided by 16 centimeter cube. So now, but we have to give this volume in decimeter cube. So 1 centimeter cube is equal to, so 1 centimeter cube is equal to, so basically 1 decimeter cube is equal to 1000 centimeter cube, and 1 centimeter cube is equal to 0.001 dm cube equal to 1 centimeter cube. So you'll get concentration in mole per centimeter cube, and you just divide it by 0.001, you'll get the concentration in mole per dm cube. So if you do it, you will simply get 0.9765 moles per decimeter cube. So this will be your answer. So moving ahead, Part F, it says describe and explain what happens to the gradient of the straight line for first 4 points on the graph if a metal cup is used instead of a plastic cup. So remember, we are measuring the temperature here. If there is a metal cup, metal is a good absorber of heat. Metal will absorb some of the heat, and the rise in temperature or the temperature measured by the thermometer will be less than what we are getting. So the graph will eventually will have less slope. So if we are going to see this graph, I'm going to use say green ink. So what will happen? So the same volume, for example, will give you less, somewhere here, with less change in temperature, uh, somewhere here, or somewhere here. Okay. So for a metal cup, the graph will be, the slope of the graph will be different. It will be, or the gradient of the slope will be much less compared to the earlier. Okay. So getting back to the, so I'll use look the gradient of the slope will decrease as the metal absorbs some of the heat released during the experiment. This is because metals are good absorbers of heat. Okay. So then part G, it says a burette may be used instead of a measuring cylinder to measure the volume of water in this experiments. Suggest how this improves this experiment. So burette is generally a more precise measuring tool compared to a measuring cylinder. So burette will provide more accurate and precise volumes slash or reading of the readings of the volume, precise readings of volumes. You can say that. Now, measured volumes. Okay. And it says part H state the dependent variable in this set of experiments. The dependent variable, remember in the graph, this is your dependent variable, and this is your independent variable. General um, criteria of making graph. X-axis comes on the is the x on the variable on the x-axis is your independent variable, and variable on your y-axis is your dependent variable. The dependent so dependent variable, so rise in temperature. Okay, rise in temperature is your dependent variable, or you can call it a rise in temperature, or your graph says temperature rise. It's a better way. So temperature rise, good way to write the actual variable name that is given to us. Temperature rise slash degree centigrade is your the right, the actual dependent variable. So moving ahead, question number 3, it says the student investigates solid Y and solid Z. The solid Y is white and contains carbonate ions. Test the test the test the solution the student does on Y are shown in table 3.1. Some of the observation of these tests are also shown. First test, it says add excess dilute sulfuric acid to Y in a boiling tube, or basically heated boiling sulfuric acid is added to Y. Effervescence and solid disappears. Effervescence is something, or is a gas. It means that the gas is released, and effervescence occurs when you have carbon dioxide gas. And the acid, it means that the acid and the solid disappear. So whatever the salt Y is, it contains a carbonate ion, and it also dissolves in sulfuric acid. So this is something. Um, so you can say salt Y dissolves in warm slash heated H2SO4 and contains a carbonate ion plus carbonate salt. It's a carbonate salt. So this is one thing is clear. Then it says part 2, it says adds aqueous sodium hydroxide to the solution from test 1 until a change is seen. So now whatever the solution is, you are adding dilute sulfuric acid to it. Oh, sorry, aqueous sodium hydroxide to it, and then there is a formation of a precipitate. It means that when you add to the solution of this carbonate salt, you add NaOH, you'll get some sort of precipitate and some of the so white precipitate. It means that once this so salt dissolves, it means that whatever that carbonate salt was, it was now a sulfate, and that sulfate reacts with aqueous sodium hydroxide to make a white precipitate. So add aqueous sodium hydroxide to mixture from test 2 until but no, until a further white precipitate. So even in excess sodium hydroxide, this white precipitate dissolves it soluble in this NaOH. So this is something we need to see. So predict the identity of the gas. So first gas we have also already done. It's the carbon dioxide gas. Now let's give some space here. So carbon dioxide gas, CO2. Test and observation. Pass the gas through a test tube containing lime water. It turns milky. Okay. Then it says the solution produced in part test 1 contains an anion. Anion. Okay. Name the reagent that reacts with an anion to form a precipitate when added to a solution produced in one after the addition of dilute nitric acid. So dilute nitric acid is HNO3. So remember, instead of H2SO4, now you're adding nitric acid. So once you add nitric acid, so nitric acid, it will form with an anion to form a white precipitate when added. In presence of reagent that reacts with the anion to form a white precipitate. So this, or again, this is basically soluble salt. So remember, generally all nitrates are soluble, and white precipitate, you're going to see the end, um, um, you can say, the last two pages, page 15 and 16 of your exam paper. You will find out the different names of anions and cations, which are which are used. So anion will be, you can say, um, nitrate, or you can call it anion is actually, this is basically negative ion, are anions. So anions generally are, you can say, nitrates, sulfates, 2,4, or you can say chlorides. So these are your anions. So what we are talking over here, the precipitate that is forming, that is basically a soluble precipitate, and all nitrates are soluble. So in our anion will be um, something of, you can say, is a nitrate in nature. And generally, a white precipitate, we are going to see uh, the salt that gives us a good, or is a safe salt that can give you an always white precipitate, is a barium salt. So the good answer will be, so barium salt is blue, and nitrate is 3 negative. So it would be uh, barium nitrate, BaNO3, uh, 2 negative, I think. Oh, what happens? 2, or just simply, instead of the chemical name, it's good to write the actual name, that is called barium nitrate. Okay. Then it says the observation for test 2 are incomplete. State one observation the student makes. Um, sorry, the observation in test 3 are incomplete. State one observation the student makes in test 3. So let's see. It says white precipitate dissolves. The other observation is plus a colorless solution appears or forms. Okay, so once your precipitate actually dissolves, the whole test tube or the solution inside the test tube becomes colorless. Look, one observation the student makes in test 3. Uh, a colorless solution is formed. Okay, and it says solid Y contains only one cation. Okay, so solid Y contains one cation. The student cannot identify this cation from the observation in the table 3.1. So use table 3.1 to name two cations which would or which could be present in Y. So remember, if we have a solid Y, so let's think out loud. So solid Y, so we know that this is a carbonate salt. When acid is added, carbon dioxide. So it is a Y. So I call it. It has a Y positive ion plus a carbonate, um, CO2, calcium carbonate. Forgot the carbonate, CO3, 2 negative. Ah, ah, ah. Y has one cation and CO3, 2 negative. So this is something Y. So Y would be Y, um, X. You can call it Y plus this A9. So not call it a plus. It can be 2 positive. It can be 1 positive. It can be 3. It can be any salt. So it is one. One is Y. And once effervescence is this, so this Y completely dissolves in sulfuric acid. So which carbonates are generally dissolved, and then uh, it forms sulfate, and those sulfate when, for example, sulfate salt plus NaOH will give a white precipitate. Okay, so generally these two are, you can call it as zinc and aluminum. So zinc and aluminum are two, you can say, cations that you can say are soluble in aqueous sodium hydroxide. They produce white precipitate, so and eventually a colorless solution. So these are two things, or the two salts which we can distinguish. So zinc 2 positive plus Al3 negative. So there is a chance that Y can be zinc carbonate or aluminum carbonate. Okay, so this are two, and you can also use the page number 15 to see the effect of aqueous sodium hydroxide on aluminum and zinc, and you'll be able to easily shortlist those two salts as the ones that can be used. So name two cations. They are zinc. Oh, ah, zinc. You can call it as Zn2 positive, and aluminum Al3 positive. It says describe an additional test the student undergoes on the solution produced in one to identify the cation Y. So the easy test is simply add aqueous aqueous ammonia to the solution until a change is seen. Okay, so seen, you can also say record this change, then add excess aqueous ammonia and again record the observation or change. So this is the test. So this test will basically provide you good information of whether uh, it is aluminum salt or a zinc salt. Remember that aluminum is insoluble in aqueous ammonia, and the zinc is soluble in aqueous ammonia. Once you add them in excess, aluminum precipitate remains, whereas zinc precipitate dissolves in excess ammonia and a colorless solution is there. So this is a good test to differentiate between these two anions. So it says, then part C, solution Z contains one cation and one anion. The cation contains two non-metals. So cation contains, remember, two non-metals. Okay. The student adds aqueous sodium hydroxide to Z in a boiling tube. Describe how the student completes this test to identify the cation in Z. Okay, so one cation, one anion, the cation contains two nonmetals. Okay, so just simply, uh, first of all, the student adds, so this is your test tube, so this is your salt Z or solution Z. Sorry, for example, this is my solution Z. This is solution Z. Add NaOH. Okay, so first of all, when you add sodium hydroxide in a boiling tube, First of all, warm the mixture. Okay, so, so there will be a gas will be released. Okay, test the gas with damped red litmus paper. So if the litmus paper turns blue. Okay? So if it turns blue, it means that ammonia gas is released and NH4 positive ion is present. Okay, so this is a good way to check this. Right. Then it says student adds dilute nitric acid and aqueous silver nitrate. Remember, this is AgNO3. AgNO3. This is dilute sulfuric acid to Z. So the Z, one of the cases SO4 plus we don't know what is here. Okay. A precipitate is formed. It is difficult to tell if the precipitate is white or cream in color. Describe how the student uses separate aqueous solutions of a chloride and a bromide to decide the color of the precipitate. So you can say pour um, the solution into separate test tubes. So now you'll have two test tubes. Use one test tube to check for chloride ion and the other test tube to check for bromide ion. Well, that's it. So you just have so describe how the solution uses two separate aqueous solutions of chloride and bromide to decide the color of the precipitate. Okay, so this is then it says the students add dilute nitric acid and then aqueous barium nitrate to Z. So dilute nitric acid HNO3 plus barium nitrate. So barium nitrate is a soluble nitrate salt to Z. This is an ammonia. Expect that. So what will happen? So nothing will happen. So barium is soluble, or the precipitate will be formed in this case will be again a soluble precipitate. So um, no change is observed. Observed. Colorless solution will be there. Okay. So this is how it goes. So moving ahead to the last question of the paper, so it says copper 2 sulfate is a salt that used to kill pests on plant leaves. So copper sulfate, CuSO4, copper sulfate. Copper sulfate is prepared by neutralization of dilute sulfuric acid, H2SO4, with solid copper oxide, CuO, copper 2 oxides, okay. Plan an experiment to prepare pure dry crystals of copper sulfate. Your plan should include the use of common laboratory apparatus, means test tube, burette, funnel, flask, measuring tools, or measuring apparatus. Then dilute sulfuric acid solidly. No other chemicals to be used. Your plan should include the apparatus needed, the method of use. You may diagram to help your answer. Okay. So first of all, we have to basically write this. So basic. So let's start. It says step one will be take H2SO4 in a beaker and warm it using a Bunsen burner, or using a burner. Add copper oxide in the sol- in uh, the beaker containing warm H2SO4 and stir it using a glass stirrer. Okay. Or stir it using a glass beaker. You can say till CuO dissolves completely. Okay. Then add excess CuO and stir the mixture. Repeat the process till CO2 remains in excess. So you have to keep doing it till no further CO2, or sorry, copper oxide, CuO, dissolves in the uh, solution. Then once it is done, of course, filter out excess CuO using uh, filter paper. The solution is left to okay. So now your solution does not have any excess CuO. Now what you will do is heat the solution, um, and evaporate the water. We now keep on heating the solution and evaporate the water until um, it starts to crystallize. So once it starts to crystallize, you have to stop heating and allow it to cool at room temperature. Stop the heating and allow the mixture, or not mixture, solution to cool at room temperature. Remember, cooling is very necessary in making crystals. If you slowly cool at room temperature, you will get big crystals. And if you rapidly cool, say you put it in a fridge or a refrigerator or you can say a freezer, it will um, it will rapidly cool. And what will happen is that you will not get very good crystals. You will get decent or a very small size crystals maybe. Uh, so allow it to cool um, at room temperature to form crystals. Okay, so once you see crystals are formed, dry the you can say solution with crystals using a filter paper. Filter paper and remove the filtered crystals from the filter paper. So this is how you'll make good crystals of copper sulfate. Remember, these crystals will be blue in color, and copper sulfate is poisonous. So do not ever think of, you know, drinking or even touching it, or I mean, stay away from this salt as far as you can. It's pretty dangerous. So that is how, again, the crystals of copper sulfate are formed. This is the last question for this exam. So I hope you were able to understand and you have learned something from this video. And I wish you best of luck for your exams and preparation for this subject. So see you next time. Take care.